Hobart School of Welding Technology presents Training in Oxy-Acetylene Welding, Cutting, and Brazing. Topic number 9, Lecture Discussion. Weld Quality Inspection. The objective of this topic is to be able to identify weld defects, their cause, and their prevention. There are 6 factors that must be controlled in order to make a good weld: flame, joint preparation, torch angles, travel speed, inner cone distance, and filler rod addition. Without proper control of these factors, weld quality cannot be assured. The flame must be adjusted to suit the requirements. A carburizing flame is used for most brazing operations. A neutral flame is used for fusion welding. And an oxidizing flame is used for braze welding. Fuel gases must be mixed properly. Too much oxygen for the acetylene flow produces an uneven weld bead when welding steel. There will be no sign of the even ripple found in most quality welds. Gouging may occur along the bead edges. The excess oxygen makes the flame too hot and can cause excessive melt-through. On the other hand, too much acetylene for the oxygen flow will produce a carburizing flame, which causes a porous weld, contaminated with carbon from the flame. The weld has a grayish, soot-like film over it and may be covered with spatter from the excessive sparks. The root side may be extremely porous and also contaminated with carbon. The gas pressure and the tip size combine to control the flow rate and therefore the amount of heat. A neutral flame from a proper orifice size, but with too strong a gas pressure, will form a deep puddle and probably burn holes in thin gauge metals. The same flame with correct gas pressure, but with too large a tip size, may add too much heat to the metal. In both cases, the temperature of the flame remains the same. Only the amount of heat changes. This is similar to adjusting the flame of a stove under a pan. The greater the gas flow, the more heat goes into the contents of the pan, even though the flame temperature hasn't changed. When welding with too little gas flow, the rate of heat input to the work is too low, and this produces a narrow weld bead with occasional loss of the puddle. The heat is conducted away, keeping the weld area too cool, in spite of the fact that the flame itself is hot enough. To correct for the rate of heat loss through the metal, it is necessary to use a larger orifice size and higher gas pressures for thicker metal. It is possible to vary the pressure somewhat for a given orifice size, but there is a limit. For example, if you have selected too large an orifice for the thickness of the metal and try to correct for it by reducing gas pressure, the flame may pop or go out. The result will be a poor quality weld. Proper flame control must be accompanied by proper technique to produce good welds with a smooth, even ripple, even edges, and proper fusion into the joint. If joint preparation is not correct, a poor weld will result regardless of technique. A butt joint in thin material should have a tight, even root opening. As thicknesses increase, it is necessary to provide a larger root opening to ensure full penetration. However, too wide a root opening can cause melt-through and poor fusion to the root side. Over a certain thickness, about 3/16 inch, it is necessary to bevel the edges of the joint. Using a larger tip alone is not the solution for obtaining full penetration. The material would merely overheat. Similar conditions apply to fillet welds. Joint design must be carefully considered to produce the desired strength or condition of the weld. On both T and lap joints, the material must be tightly tack welded to prevent heat from flowing under the top plate and causing undercut or underfill. Beveled plates should be smooth and consistently straight. A roughly cut edge is difficult to weld and results in poor fusion and lack of penetration. The work and travel angles of the torch also play an important part in the quality of welds. In a fillet weld on a corner joint, improper work angles will result in undercutting. An angle aimed too much at the bottom plate can cause undercut along the top toe of the weld. A travel angle that applies too much heat ahead of the puddle enlarges the puddle and produces a flat weld bead with insufficient reinforcement. This may also cause the filler metal to stick to the work. There is a narrow range of travel speeds that will produce quality welds when all other conditions are within the desired range. Too slow a travel speed results in weld beads that are too wide and concave. On butt joints, slow travel will result in excessive melt-through and too much reinforcement of the root. Too fast a travel speed results in loss of the keyhole and a narrow convex bead with poor penetration and poor fusion at the edges. This will also cause insufficient penetration at the root of open butt joints. The inner cone should be held the correct distance from the work, normally 1/8 inch. Holding the cone too close to the work causes poor weld appearance or gouging, and the flame may pop or go out. On the other hand, holding the inner cone too far away will reduce the amount of heat to a point where the weld becomes excessively convex with poor fusion. Filler metal must be added in the portion of the puddle that is hot enough to melt it. Touching the rod to colder areas will result in its sticking to the work. Poor appearance is the usual result. Not adding enough filler metal may result in undercut or underfill of joints. Too much filler metal is wasteful and produces a weld of poor appearance with excessive reinforcement. To some degree, you can correct for one improper condition by varying another condition, but it is better to have all conditions as nearly correct as possible. Time spent assuring correct control of the 6 factors is time well spent.